right, everybody. Hopefully, I just realized you all can hear my mic test there. Um, but that's hacking. It can you can have a technical issue sometimes. I was just on stream. We were doing our no light presentation, and I was looking at all the websites by myself. I didn't realize I was looking at them by myself, but yeah, forgot to share the screen with all of you. But it's really great to be be seeing you all in there. And thank you, Google AI ML, for confirming that the mic is working great. Yeah, it's so awesome to be with all of you here. I'm so lucky that I get to be a part of this community and learn with all of you. So yeah, have IMS Nos join Python Pros for the Python knowledge Unity and movies. I think this is from Nathan's stream. What an awesome stream. Yeah, I'm so impressed with all of the animated Bilhages, and just in general, always does an incredible job for Global Hack Week. So hats off. Google IIML asks, how can I become a part of MLH? Well, you're a part of MLH right now. You're part of our community, and we keep so much of our community accessible and free to join. But I think I know what you may be asking is how to actually join MLH, some kind of a role. And I'm happy to send you a link to that. So I'll send that in the chat in case you're interested in applying. Not sure exactly what roles are available right now, but that is where to find it. Hi there. Hi, I am Snos and Rohit. Hi, good to see you. Thank you for joining today. This is the final part of our workshop. And hey, thanks so much for posting that check-in link. I really appreciate that. I almost forgot myself, but I am, as Nos just sent that check-in link in the chat. I'll send it one more time just for good measure, so I can also put it right up there on the screen. This is going to be the last series of our Earth Engine workshop. And yeah, it's so awesome to see you all here, staying till the very end. And the reason we want to use the check-in link is because it's going to give us points for your guild, and beyond that, it also lets us know what kind of content y'all are interested in. So definitely check in if you are able to. Yeah, and I mean, you can win swag during Global Hack Week. You can get to the most points of any guild. So those are some great reasons that you can check in and participate. Yeah, exactly as Rohit says, to get the attendance. All right, well, folks, now that we are on our way, we're gonna pick up where we left off last time. You might remember that last time we were dealing with Google Earth Engine, and we were using the code editor to access the API. And yeah, this API is one provided by Google, and they are connecting you on your personal computer. They're connecting you with their servers and all of the wonderful Earth data that's hosted on their servers. And yes, last time we had a cool presentation, so you can go ahead and check out the presentation on your own. But there it is. There's my screen showing what we did last time. And you'll see we were able to actually fit a harmonic model to our data. And the reason why we call it a harmonic model, which is this red curve here because it is periodic. So every year, the crops, they grow and they get harvested, and that's kind of how we can fit this regression model. But then if you look at a place like an urban environment, you can look at Bloomington, for example, which is a medium-sized city in Illinois. There's no similar change in the vegetation there, because most of what is there are buildings, and buildings won't change in the same way. They might get some snow on top in the winter in Bloomington, but most of the time they will be the same. So for that reason, we're fitting these harmonic regressions to try and predict what kind of cropland or urban environment might exist in a given region if we have those vegetation indices as an input. All right. So let's go ahead and continue along with this. And we're going to, before we move on to classifying those crop types, we want to add CDL as a band to the harmonics image that we created, and export that image as an asset. So because we are able to store all of this information, we can then use it later. So that's a really good reason why we want to add this as an asset. So we're going to make a comment in JavaScript, add CDL as a band to the harmonics. And so we're going to create a new variable like we learned how to do earlier in the first workshops. And it will be an image object, an Earth Engine image. And we're going to concatenate, use the CAT method for our harmonics and our CDL bands. So here's our harmonics. You'll see it up here. It gets those harmonic coefficients from our Landsat data. And the bands that we're getting from Landsat are these, which are, near infrared, shortwave infrared, things like that. Wow, my mouse just broke. Not to derail the stream, but that's never happened to me before. Okay. I think I was able to put it back together, but yeah. Hey there, Indigo Wizard. So if y'all haven't met Indigo Wizard in the chat, a very expert GIS coder. So hopefully, if you have any questions, you can ask me, but you can also ask the community. We have so many really talented folks in our community who are super helpful. Yeah, we're just going through what we did last time. And again, we took these bands of light. These are bands of incoming radiation from that satellite, Landsat, and along with our GCVI index, which is sort of a combination of different bands. And we used harmonic regression to get some information about their periodicity, like we can see on this plot here. And yeah, that's kind of what we were doing yesterday. Was building out all of this functionality, not trying to scroll too far up, but I did want to point out a few things we did last time. We added a mask, and actually we're going to be doing masking as well today. So if you forget about masking, go ahead and check out our function add mask from last time. This NEQ and EQ stuff is pretty important for those. In the study area over here, we were using this Tiger data set, which is a feature collection. And if you remember from last time, feature collection is a way to get the counties, state boundaries, country boundaries. So if you're interested in that kind of stuff, it's great to see. And yeah, let me look in the chat here. So impressive that folks are having such a high attendance of the sessions. I'm so glad that you're enjoying it. And as IMS No says, make sure to sleep. Um, it's awesome that you're attending. We also want you to sleep. So great. Thank you for saying that. And yes, lots of corn, soy, and soy and corn. Corn and soy and soy and corn. That's pretty much what the Midwest is about. Let me show you all actually where I used to live. Um, I used to live in this state over here in Iowa. And Iowa is a very agricultural part of the United States. It's not very far from our study region today, which is in Wilmington. I've been to this town before, actually. They have a university there, and yeah, it's a very nice place. And they do have lots of corn and soy and corn. But anyway, let's move down. And like we were saying, we're going to add CDL as a band to the harmonics so that we can keep all of this data together. So you could think of the harmonics as our fitted to the data, our model that we fit to the data, and the CDL as the truth. So the CDL is the true classification of those land pixels. So our harmonics may predict that there is soybean somewhere, but our CDL is going to tell us for sure whether or not it's there. Okay. So we're going to now export this image to an asset, and we're gonna do that. But before we do that, let me send a link to you all. It's going to be a link to the textbook that we're using for these sessions. So I'll send that right in the chat, and I'm going to put it up on the screen as well. Firstly, because it's important to have access to this book. It tells you about how to get the code. If you are having trouble following along on the screen, all of this code is available on their website through their textbook. And you also, it's good to acknowledge our sources. So, we are using a chapter of this book, which is the first chapter, and it's written by Sherry Wong and George Azari. So thank you both of you for creating this resource for us to learn together in our community. And yeah, some folks. It was a very nice Illinois town. Yeah, exactly. The Midwest is known for being very nice. Nice people live there. And yeah, definitely visit Iowa if you go to the US. It's kind of out of the way though. So depending on where you're visiting. If you're visiting Chicago, it's super easy to get to. The world's largest truck stop is in Iowa. And it's a huge, huge building with lots of trucks. Big fuel station, big food court, big gift shop, right on the border of Illinois and Iowa, and definitely worth a look. But yeah, I'm also looking in the chat, some folks saying how they liked all the streams that they liked, and it's great to see that you all enjoy. And yeah, thank you for being here with us. Well, let's move on to our coding today, and we're going to put up Greene County Harmonics as the name of this asset, we should say, and we're going to use the export function to export this image, this Earth Engine image, to an asset, the one that we created through concatenation above in line 233. So to do that, we'll give some dictionary key value pairs. The first one being what the image name is, which is Harmonics Plus. We'll give the description, and for this, we'll just use the file name. And you can put whatever file you might want to put here. So you could just call it test. You don't necessarily have to put anything there. I think you can even just leave it empty, and it will. Well, no, I think you have to give some kind of file name, and then your asset ID will be the path to the asset that you want to create. You can just use the file name here as well. And the dimensions variable is null for this one. We only want to use the region over McLean County, so we'll do that. We want to keep our scale at 30, which is the resolution of Landsat. And our max pixels helps us keep the size of the file manageable. And so this will export the image. Yeah, so there you go. Not sure why it gives a little, oh, that's right, because it's harmonic plus. I guess in the actual file, it is harmonics plus. And here it is, so we can get that asset. I should really change the name of that one. Anyway, let's continue along, and we are going to now try and visualize our harmonics. And so let's go ahead and do that. We're going to create a new variable called visImage, and it's another concatenation of our previous images that we've created in Earth Engine. So the first one is going to be one of the bands from our harmonics, and it's going to be 3 GCVI cosine. The next one is going to be harmonics.select 3 GCVI sine. So we're getting all of the different bands from our image, and we're not actually going to use those cosine 2 and sine 2 features, because we're going to make 3 classifications, and so we're going to use these 3 to do that. And you know, if we were to plot these right now, let's try that actually. We would just want to do map.add layer to add this layer to our map. And yeah, we want to give some kind of minimum and maximum value. I don't know if these are going to be sensible, but then we can give some kind of name to the layer. We do that, we get a new layer on top of our previous one. Harmonic coefficient, false color. And kind of hard to see right here. Probably the reason is that our coefficients are all going to be very different values, and maybe this minimum and maximum was not a good choice for it. So let's optimize these coefficients to be visualized, and we're going to use the preset values that the textbook gives us. The textbook says we should just divide all of these constants by 7,000. Probably if we were to move this maximum up to like 10,000, we would start seeing something. But let's divide by 7,000 to kind of bring everything down, all these coefficients down. See what happens. We'll move this into, say, 0 to 5 for now, just to see what it looks like. See if it's getting any better. Yeah. Still not that good, but you can actually see the difference between them. You can see some black and some blue and some light blue. If you're able to see that contrast, which not everybody can, so because it's a really small contrast. But now we're gonna shift these over by a little bit. So for the first cosine layer, we're gonna add 0.6, the second sine layer, we're going to add 0.5. For the third constant layer, we're going to subtract 0.6. We're going to change our bounds so that it's minus 0.5 to 0.5. And we'll turn off our other layers. So all we see are our false colors. And you can see it there, the little colors of our different land use types. So the yellow in this case is going to be, our urban areas. And so that's where our urban areas are really shining out. Those are places where, the periodicity is not going to be too significant, like it would be with crops or vegetation. You can also see some blue, some light blue. I think that's probably rivers or roads or something. And then if we scroll in a lot, you can see that these different plots of agricultural land have different shadings. Some of them are very light, closer to the urban area, and some of them are very dark, this dark purple blue color. So we're going to see if we can train a machine learning algorithm to detect which of these are soybean and which of these are corn, based on these harmonic coefficients. It's going to let us see the differences between them. So now we're going to move on to our classifiers. And, we did a whole classification. Workshop series back in AI Week in February. So if you're interested in learning more about classification problems, check out that video series. It has some really good algorithms, including, I think, random forest, which we're going to use today, some k-means clustering, which is actually a clustering algorithm, but still sort of categorizes things. And we also studied Markov decision process back then. So there's a few different classification algorithms that you could look into if you're interested. But today we're just going to use a pre-created random forest classifier. So let's define a random forest classifier. And it is built into Earth Engine. So we're going to use the SMILE random forest model. Okay. So random forest, if you're not familiar with it, let me give you a quick introduction to random forest. I'm just going to look at their website because I think it'll have a really good visualization of what a random forest is. And you can see here that a simplified version of random forest is that the model will create a bunch of different decision trees. We call it an ensemble of decision trees. And then all of these decision trees, which sort of make different decisions at their nodes, which are these circular things, based on some threshold values, they will then vote on what they think the classification of something should be. So in this case, this first tree voted that, it went through its decision tree. If it kind of decided that whatever this data was, it's a part of class A, which we could just say that's corn in our case. And decision tree 2 went down that, a similar type of thing, but they came out with a different outcome at the end. So that would be class B or soybean. And then decision tree N came out with soybean as well. And so in the majority voting, they would decide collectively that this would be soybean, because the corn kind of got outvoted on that. Okay, so that's what we're going to use today in our workshop. We're going to stop to take a few questions. And so is it based on corn or soy density? So that's a really good question. And I'm not agricultural scientist, but I do know that in the in the textbook they say soybeans and corns have a slightly different growing cycle. So because of that, when you do the harmonic regression and you find the season of their growing, you come up with a slightly different answer depending on whether it's soybean or corn. So I think that's the reason why the classification is like that. But you can add more features actually to your model, to your random forest model. And generally speaking, it should improve the accuracy of the model. So if we think that could be a good feature to add, that would be a great project to do in the future. This is a great suggestion here about cartography. Whatever you're visualizing, if you have a presentation, just use a color palette between blue, cyan, and purple magenta. Okay, actually, I think that seems like a joke. You got me. That would be pretty terrible. I was like, oh wow, that'll be a great suggestion, but no, I don't think so. Let's think. Maybe that would be like bubble gum or something with blue and the magenta. Yeah. So anyway, let's continue to move on, and yeah, we will go to this tab instead, which is the Earth Engine one, and we'll continue along with our random forest classifier. And so let's go ahead and add some properties to this model. So the first one is number of trees, and number of trees tells us how many of those decision trees the model will create that will kind of vote on the outcome. And we'll set that equal to 50. We could even set it equal to 100 if we wanted to, but let's just keep it at 50 for now. It'll run a little bit faster. And we also are going to set a minimum leaf population. So this kind of seems confusing. What is a minimum leaf? What does that mean for our model? Well, it will mean that if you want to create a new branch to the decision tree, make sure you have at 10 minimum data points in that new decision, in that new node. So if there's not at least 10 in that node, let's just not create a new just like branch on the tree. And the reason why you might want to do that is to prevent the model from overfitting to the data, because you don't want to create a special category for just one data point in the decision tree process, right? So it just keeps the trees generalized, modeled like that. Anyway, then we'll also add in the seed property, which is just going to start the random forest off at a random point. So that's kind of the purpose of the seed. Now we're going to get the harmonic coefficient band names, which we already defined earlier, but we can do that by typing harmonics plus dot band names. Tell us what the different bands are in that Earth Engine image object. And when we do that, we can choose to remove the CDL band and the system index band, because those are not going to be what we want for right now. Because we're not going to necessarily use those as training features. So now we're going to prepare the CDL band to be the output of classification. So we're going to remap the crop type values in CDL to corn. So as 1, soybeans as 2, and everything else 0. So let's do that. Because remember, we're not interested in other kinds of crops. We're only interested in corn, soy, and other. We'll just categorize everything else that way. Take our cropland band, and we'll say equal to 1. our harmonics plus cropland would be equal to 5. So this would be soybeans in the original CDL classification. But we're gonna go ahead and multiply by 2 to convert soybeans to classification 2. So we just converted, in the first section here, we just converted our first classification value, which is just straight corn, into 1. And then we put the soy, which used to be 5, but now we're going to convert it to 2. And the rest of them we will just leave at 0, which will be done by the mask. Yeah. So now we will be moving on to Sorry, I always think I need to sneeze when I'm on camera. Okay, so we'll be moving on to sort of tack this along into our image. Let's make sure we're writing harmonics plus here, otherwise we're going to get stuck. Right? So we've just transformed the CDL band into 3 classes instead of 5 different ones. And so that's going to help us simplify our model and just look at corn, soy, or other land types, right? So that's the purpose of this section of code right here. Try and reorient this a little bit so it's easier to see. Just for now, get rid of that stuff on the left-hand side. Okay, so for those of you who have done classification algorithms, you might know this already, but for those of you who don't, that's okay. We need to actually set aside a certain number of points in order to train the model that we're going to use to discern corn and soybeans and other land types. So let's set those aside. Okay. So we're going to sample from the data set in the geometry of McLean County, our 30 resolution, and 100 data points is how many we want. So that's what you put in the sample method. And we can just write a quick print script to see if our training points printed out. Excuse me, if they got sampled successfully. Let's run this here. It takes a little while now. We're doing so many different things in our code. It really does take a little bit of time, but it'll populate in the console here, those training points as a feature collection. Yeah, exactly. I think that's correct, honestly, Indigo Wizard. If someone's looking at you, you can't sneeze. And I really thought I was going to sneeze, but I think it's all of you helping me out to not sneeze. Anyway, while that feature collection is spinning up, we're gonna train the model on this training data set. And so really what this means is that we're going to expose our random forest model, which we constructed up above. We specified what we wanted it to look like. We're going to train that by calibrating it based on this sample data set. We actually, it just loaded just now. So we have all of our features in here. And yeah, you can look at that and see. These are the different bands and their different harmonic regressions. And it then tells you what kind of cropland it is. So this is one. And for those of you at home who have been paying attention, you'll know that one would be our corn band. So this particular feature is associated with corn. And our model is going to try and predict that using the harmonic regression coefficients. So let's look into that. We're going to use the train method. And the train method takes our points as arguments. And we'll write cropland, which is the band that we're actually going to train to try and classify. And the bands will just be the features for those. So you can see we define those as the features for this model. We're also going to create a little confusion matrix. And I'm not sure if you all are familiar with confusion matrix. Let me show you the Wikipedia for confusion matrix. It's really good. They have a really good image there, which kind of specifies confusion matrix. All right, so y'all can see there that this would be an example of a confusion matrix. So let's say that you predict positive, like maybe this is some kind of test for an illness. You predict positive. If it's really positive, then you get a true positive result. But it's possible that you take a test and it tells you you have an illness, but you actually don't have the illness. And that would be a false positive. So we can get all these different possibilities and they will populate a confusion matrix of the model. So yeah, here's just an example. We're going to see an example like that with our model instead of a test. So it's kind of like taking a test for an illness, except in this case, we're going to be using a model to predict the cropland. Let's see whether it can do that correctly or not. We're not going to make the crops take a test. All right, so we're going to use the confusion matrix method on the model. And we're going to print out the training error matrix. And we're going to print out the training overall accuracy, which is going to be just kind of a sum of those, of the a fraction of however many predictions were correct. Okay. So I'll just go ahead and sum all of the correct predictions, which are along that diagonal of the confusion matrix, and then sum and then divide that by 100 essentially, because we have 100 samples. So let's run these and see what we get. While we're waiting for that to run, I'm curious, is anyone in the chat oh, sorry about that. Did not, thank you, Indigo Wizard, for letting me know. But we should be good to go. So yeah, was just basically applying this confusion matrix code to our data. And Earth Engine is pumping away, trying to get our confusion matrix. You can see actually there it is. There it is. So this diagonal is all of our correct results. So we can actually figure out what the accuracy is if we add up all of these. Should be pretty good actually. Something like 90 out of 100. But certain categories it did not do as well. So sometimes it predicts that the category is other, but really it's corn or soy. And, we just, we can't really do much about that right now, but some of the things you can do to improve that accuracy are, adding in more features that are relevant, like IAM-SNOS suggested, and maybe using a more complex model or a better suited model for the problem. You never know what's going to help produce that increase that accuracy. Anyway, let's go ahead and now explore how well these results will generalize to the entire region. So in our training data set, we just looked at 100 pixels sampled from McLean County. Now we're going to apply our model to the entire county and see if the calibration that we did with these first 100 points was good enough to give us good accuracy across the board. So we're going to sample a few more points that are different than the training points that we created. So we're going to sample test points and apply the model to them. These are points that the model has never seen before. It calibrated itself based on the training data set, just a small fraction of the entire region. Let's see if it can do the same or just as well on this new 50 points. And the way that we test it is by using the classify method. So you can use classify in the model on any set of sampled points, and it will predict for you whether that region is full of corn, soybeans, or something else. All right, so we run that, it would give us the test results. And we can compute the confusion matrix as well with our test data. So let's do that. I'm going to compare cropland, which is the true data, to our classification, which is where the results of the test are stored. It's up to us to see whether this data was saved, or I'm sorry, was as good as the training data, or maybe it's worse. Who knows? Well, only time will tell if we can get as good of a result. All right, there we go. And you might ask, why would we do a validation, a test on another 50 random points? And the reason for that is it's just much quicker. I mean, you can see how much time it takes the model to even train on just 50 points through Earth Engine. And we don't want to waste our computing resources by doing the whole region more than just once. But while that's compiling, let's begin that process of applying the model to the entire study region, because we're going to eventually want to do that. Let me put that link back up to the textbook for those of you who are not there yet. And check this out. Here's our test error matrix. So we sampled 50 points, and 38 of those were correct. So it's an accuracy of like 86%. And that's lower than our training data set, which was basically 90%. But it's not too much lower. Oh, 76%. But it's not too much lower, but it is lower. And the reason for that is because we overfit our data. So yeah, unfortunately, most models will suffer from that, where your test accuracy will not be as good as your training accuracy. But 76% is still pretty good. And we can, now that we're satisfied with our test, move on to classifying the whole region. If you're not satisfied with your test, there are a few things you can do. You can increase the size of your training data set. So we only used 50 data points for training, which might not be representative of the entire county. You could imagine that someone would say, oh, you need to really sample more data points because 30 of those data points were in the same farm. It's unlikely that would happen, but it's possible. So if you increase your sampling in the training data set to like 100 or even 200, it could help with that. The drawback to doing so would be that you would unfortunately have to spend a longer time training, because your training is going to take longer the more data that you use to calibrate. So that's totally a possibility. But anyway, this is how we apply the model to the entire study region. And you can see that we're actually selecting the bands, which are the features from the harmonics plus image, and we're going to classify the entire thing. So we're then going to use the prediction palette, the same one that is used by CDL, to say 0 is gray, 1 is yellow, 2 is green. That's kind of one way that we could classify this data. All right. And we can visualize the disagreements and agreements between CDL and our predicting. So if we want to visualize agreements and disagreements between our predictions and CDL, we can do that. We just need to add a new layer to our map, and we're going to directly compare our region classified image, which is again the random forest generated predictions. We're going to use an equivalent statement to compare it to our corn, soy, other image, which was created by manipulating CDL a little bit. We'll only allow 2 values, min and max. And so when it's white, which would be 0, that means that the 2 images agree on what the value is there. And when it's 1 or black, they will disagree. Okay, so now we can run this one, and we'll actually see the prediction of the 2. See, it's starting to build our false color image. You see our classifier prediction. Let's isolate the classifier prediction once it comes in. It'll be here soon. Takes a little while. What do you all expect to see, by the way? Where do you expect the model to agree? Where do you expect it to disagree? Really curious to know. Here it comes. This is the predictions from our harmonic regression. So we're using the machine learning model to predict corn and soy, only knowing about the seasonal patterns of how they reflect light off the surface of the earth. Pretty cool stuff. A lot of corn, a lot. Our model thinks corn is very prevalent in McLean County. Let's look at the agreement between the 2. Here it comes. Yeah, so you can see the agreement between the 2 was really good in urban areas and places where there's no vegetation at all. We got total whiteness there. But outside of that region, we do get a few black regions, which indicate that basically the model that we generated and calibrated didn't do such a good job. So there are portions where it was correct, and there are portions where it was unfortunately incorrect. Right? And Indigo Wizard said less gray. Yes, interesting prediction. I agree with that. I do think there's less gray in this one. Let's look at the 2 side by side. We see all of the gray, especially in this top left corner in the classifier prediction. In the CDL, though, we don't see that. So there's a little bit less less gray. Although I suppose in CDL, these light greens would, um, they would be other. But yeah, I think you could definitely make the argument that there's less gray in CDL. Interesting. Yeah. So anyway, folks, that is our classification of the agricultural types. And if you had any trouble following along, I want you to go and look at the code repository for this one. Let's save our work. Um, and you can go to the A11D checkpoint. And this is a great place to check your work, a great resource. So please check this out. And we're going to take a quick break, just about 10 minutes. And then after 10 minutes, we'll come back and we will tackle a little bit of urban infrastructure. And we're going to look at some roads and maybe some transmission lines too in Algeria. So looking forward to that, and I'll see you all after 10 minutes. Okay, everybody. Well, welcome back, and it's great to be here with you again. I hope you had a good small break from our workshop. And yeah, you should pat yourself on the back for making it through all of these. I mean, in the first workshop, we got a little dirt on our hands. We played around in the code editor, saw what Earth Engine was capable of doing, and since then we have learned the fundamentals, and we've even done some application to agriculture. I saw an interesting comment from a little while ago. Let me see if I can remember that. I Am Snow said someone should make a food map and track the best places to eat in all the U.S. states. That would be a cool GIS project. So I'm all for it. And yeah, maybe this inspired you to build something geospatial related. But anyway, we're going to make a new file now. So we'll create a new repository. We're going to create a new one actually for EE103, which is today. And the next one we're going to do is actually on the built environment. And so this is chapter A1-3, which is built environments. So you can open that up on your own if you'd like. But we're going to create a new file in this EE103 repository. We'll call it built for built environments. And this is where we're going to put all the code for our new project. So remember, we're going to be discussing human-made infrastructure today. And that could mean anything from homes to streets, things like that. And so this is something that you can totally see from a satellite. And you remember from yesterday, maybe, that we saw the urbanization in Suzhou. So you can see all of that stuff from satellites. And so we're going to be starting with a GRIP4 dataset, which is used for calculating stuff related to global roads. So let's import the roads data. Right? And GRIP stands for Global Roads Inventory Project. So it's really neat that they have roads from all over the world. Creating first a feature collection for Africa. And you remember that features in the Earth Engine are actually kind of geometries that are associated with a place. So for that reason, this is a great tool for collecting our road data. And we will now put the same exact URL, but for North America. So we're also going to import the North American roads. And we'll do Europe as well. Sorry if we're leaving out if we're leaving out your region, I apologize. Or your favorite region. You can do this on your own with any region of interest. So yeah, feel free to swap those out if there's another region that you'd like to analyze instead. But today we're going to be focusing on Africa and in particular Algeria. Let's check the size of the data set first. And we can do that by calling the size command. When we run it, it should tell us the size of that data set. This is basically how many there are logged. So look at that. There's over 1 million roads that are logged in this data set. Pretty cool stuff. And we can repeat this twice, once for each continent. And we can just check and see how many roads they have. Uh-oh. I think it's because I unfortunately, maybe I should just do these separately with separate bars. Okay. If that works better. And likes that better. Dang, maybe these regions are not available right now through grip 4. That's okay. We'll just comment them out for now because we're only going to need our Africa grip 4 data anyway. So it's a little strange because it was working earlier. So maybe I'll go back and see why there's an error there. And maybe if someone else figures out the error, that would be good. Semicolon, you think is the error? Let me see. I think it could be, but it does seem like I have a semicolon. Let me see. Yeah, not sure, but anyway, let's skip that and try to just go with our Algeria example now. And yeah, why don't we move over there and just see what it's like over there. So we'll go from Bloomington, Illinois, all the way over to Algeria, Africa. And you can see that right there. And it's quite a big country, so I think we may see a lot of roads, which would be good for us. All right, so now we're gonna try and display the road data. We're going to do that by adding a layer to our engine. Remember, it's these feature collections objects that are really good for this type of thing because it specifies the geometry and the location. We'll just give it some color. Suggest we use 413B3A. So we now have a new layer in our map, which is going to be this feature collection of all of these roads according to grip 4. And that is almost generated. There it goes. As you can see, there's really so many roads in this region. Guessing that these areas with sparser roads are probably more rural areas. It says roads are mostly in the north coast, and the rest is mostly desert. Yeah, I can see that. See a ton of roads up here in the north coast. Seems like a nice place to visit, actually, because you have the Mediterranean Sea here. You could sit on the beach. That's pretty nice, and probably warm weather too. I know it gets kind of warm, nice and warm over there, so that's great. Okay, well, now we're going to import a country's map so that we can isolate the roads that are specifically in Algeria. And that's because this GRIP4 data is from all of Africa. So we really want to be zooming in on Algeria and those borders. Let's import our simplified countries database. And it's going to be another feature collection. And we're going to create a new function that will calculate the geometry area and add that function as a property. So let's do that. We're going to create add area as the name, and it will be a function which takes in some feature. So this could be a country, for example, and it will return as its output feature, but then setting in this this additional property, which is going to be the area in kilometers. So we're going to get the geometry of the feature, operate on that geometry to calculate the area, to get the area. And that area is actually in square meters. So we want to convert it to square kilometers. And the way we can do that is by typing divide. And we divide by 1,000 to get to kilometers, but we divide by 1,000,000 actually to get to kilometers squared. So yeah, this is kilometers squared. It's good to remember that when you're going through and doing any kind of conversion, you want to make sure that you have the units right. Always forgetting my semicolons these days. Okay, well, now we can map the area getting function over the entire feature collection. So when we do that, we can get a list of all of the areas of the countries in this feature collection, or in this database, or in this data set. So when we apply that, it will just compute the add area function over every country. And we can filter that to get the largest country in Africa. So we can figure out actually which one is the largest country in Africa. So we're just going to use an in-list statement. To basically get a list with just Algeria in it. And you're going to see the size of the country. You can even just run this. And it's working well. If you want to print out this area to the console, we can do that too. So I invite you to test that on your own. Try to print out Algeria and see what you get. But now we're going to display the country. And so we'll do that by adding a layer. And we'll do that using some kind of color for fill. This is the color that the textbook suggests. So why not? And with that, we have Algeria plotted on the map. So you can see that we were able to get that one right on the map. Pretty cool. So now we have our GRIP4 data set, which is all of the roads, and we have our feature, which is going to be this, and another feature, a second feature, which is Algeria's borders. And we can now calculate the road density of Algeria. Figure out how much road is there, and what the density would be. Okay, cool. Indigo Wizard says, I'm in a city in the north center, so I see the beach from here. I never go for a swim. That's really, really cool. Being a 5-minute walk from the beach sounds pretty nice. I would go and just walk around sometimes. Glad we have a local with us for this workshop. That's super cool. All right, well, now I'd like to sort of move on, and we're going to calculate this road density, because now we've loaded in our road feature, we've loaded in our Algeria feature. So then below is going to join these roads and the countries and figure out whether there is some overlap between the two. So let's look at that function. We're going to build it. It's going to be called road length for country. And I think you can already guess what the function inputs are going to be. It's going to take in a country and a GRIP4. So GRIP4 will be the roads, so this one will be GRIP4 Africa, and the country will be Algeria in this case. So we'll first join the roads to the country, and we'll use a Earth Engine object that we don't have that much experience with yet, but it's called a filter. And this filter in particular is for intersections. So you might know what would be an intersection, but basically an intersection is going to combine two fields and tell you whether those fields share something in common or not. So in this case, we're talking about a common geography, a common location. So if the roads and the country have a similar location or the same location, they overlap in that way, then the intersection will return true. So we're going to find the bounds for the particular country of interest. And we're going to join these two data. It's unfortunate that you got to zoom in so much for the stream. You don't get to do a lot of coding on one line, on a single line, but that's okay. We'll just make our way through it. We're joining on this condition, intersects filter. And remember that is the filter we built, which is going to tell us whether the two share a location. And now we're going to build the feature which will return our country with the calculation of road length and roads per area. We'll return in this function. We're going to kind of map a function onto countries with roads. So let's build that map. Countries with roads. And this map will accept the country, and we will have a roads list. We'll get all of those roads from the country and here. And then we will have road lengths will be the road lists, but we need to map a new function. Take a particular road feature and return the feature intersected with the country. You get its length, and you'll notice we're specifying a particular resolution on these. So that's important in any GIS application, is to be doing that sort of thing. I feel like we're missing a curly brace, but actually, no, I don't think we are. Sorry about that. Just getting a quick call on the stream. Someone really excited about GIS trying to call. No, I'm just kidding. Yeah, an area very rich in history. Definitely. Okay, so we now have to define road length. And we will actually save this as a number because it's going to be a particular road length. And we will use the reducer. So we studied the reducers yesterday. Remember, a reducer will kind of reduce the dimensionality of some object. So we have so many different road lengths in our mapper here, just mapping this onto the roads list. But then we're gonna get a particular road length, which will just be kind of the total. It's gonna be the sum. So we'll do that. And we'll convert that one to kilometers, just like we did with the squared kilometers of the country. So remember, that's kind of important to have your units all match up and be the same. And then roads per area will be the road length divided by the area. Remember, we saved that area in kilometers squared feature. We already saved that in our previous section, so we can use it now just by getting it from the feature collection. So there you go. And let's select a few things from here. Just the relevant sort of variables that we're interested in. And that will kind of discard the rest. So this is what gets returned by the function. It's road density. And let's try applying the road length function to Algeria. Okay, so we are using our function, the one we built, road length per country. We're going to use it on Algeria, and we're going to use the GRIP4 roads dataset to do that. So let's try it. Seems like we just got an error here. I wonder how we can fix that error. I think it's because I have road lengths. Always a tricky thing to do, live code. Hopefully we'll figure out the road density of Algeria. That'll be really interesting to tell all your friends. cool. I want to know the road density of the U.S. now, and I want to know all the different states that we have. I know there are some states with lots of roads and some that don't. Could be a good trivia question, actually. Hey, it seems like it worked now. So let's print the road statistics. For these sort of variables that we've asked for from the road length Algeria variable. All right. Takes a minute to compute. If the debugger knows where the issue is, why doesn't it fix it on its own? Good question. Very good question. Hard to say. I think someday maybe AI will just be coding for us. Who knows? But for now, we gotta be friends with the debugger. Best friends with the debugger. Yeah, by the way, if there's any country requests, if anyone wants to know, I guess we're only doing African countries right now. If anyone wants to know another African country and the road density there and how it stacks up to Algeria, let us know. I'm happy to do another one. I think we'll maybe do one more before we finish, one more country. And if you want to continue on after Global Hack Week playing with Earth Engine, I highly recommend you go through this textbook and check out some of the applications. There's some amazing stuff there. Indigo Wizard says, Ducky the debugging duck. I know. I'll be right back, everybody. I'm going to see if I can find a Ducky the debugger. 1 second. No, I was unsuccessful. Sorry, everyone, but I did find Frankie the file ferret. Pretty hard to see him with my green screen. It's actually kind of cool how the green screen masks out the gray, and all you can see is the ferret. Look at that. Wouldn't it be better if this workshop was taught by a ferret? By Frankie, nonetheless? That'd be pretty cool. Yeah, Frankie's clipped. Yeah, so that's from our season, Frankie the File Ferret. And he was great. You have a plushy frog named Frankie. That's pretty cool. Man, it takes a long time for them to calculate this. Pretty amazing. I hope we didn't do anything wrong. It looks good to me. I think we maybe just need to wait around a little while. Maybe we'll have a type racer game while we're waiting for this to happen. Yeah, maybe we'll play a type racer game while we're waiting for this to work. Anybody know type racer? Actually, let's take a vote. If anyone would like to play type racer or some other game, please send a message while we're waiting for this to compute. We could also play some Tetris, which we did. I know a lot of folks said that they really enjoyed the Tetris stream. So we could also play some Tetris while we're waiting. Okay, let's try a game of Type Racer, and then after Type Racer, we will try something else. Hopefully our code will compile while we're playing. All right, everyone. So use that link that I sent in the chat. We're going to use that to join a race. I'll put it up on the screen. I'm just going to do this while we wait for our code to compile. Shouldn't take that much longer, but we'll just have to see. There's also a code checkpoint that we could try. I might try that instead. Oh man, I'm losing already. Ooh, someone beat me. The blue car got me. Man, nice job. Yeah, it's kind of fun to play a little bit while we're waiting for our code to compile. Let's try another one. Just try to type as fast as you can. These tests sometimes. That's why I don't really like this one too much. But excellent. Saying we can't have usernames? We should be able to have a username. Let's see. Yeah, that's kind of lame. You can just say, "Oh, I came in second." That's okay. All right. Started off strong but lost. You're doing well though. I would say anyone who can type more than 30 words per minute, pretty fast. Or 60 words per minute, actually, I would say. Well, I'm gonna end our game here and check back on our data. Went into the textbook, tried their version. It's still giving me a ton of issues. I think it's just pretty slow, unfortunately. I guess maybe we'll never know. Maybe we'll never know how many roads there are in Algeria. Maybe there's also a lot of traffic to the Earth engine, because before, when I did this one, it was okay, actually. It didn't take too long. So maybe the Earth engine is just taking a really long time. Oh, I think it just compiled for us. Did you all see that? Look at that. We got it. Okay, here it is. The area of the country of Algeria is 2 million square kilometers. And there are 50,000 kilometers of roads. So for every square kilometer in Algeria, there are 24 kilometers of roads. Pretty cool. So we figured it out, everybody. Now you can tell your friends. There are 24 kilometers of roads for every square kilometer in Algeria. And I'm sure that there's more in the north, as Indigo Wizard was telling us. So, if maybe you could find a data set which has the north separated from the south, and try the code again, see if you can figure out the difference, or try it for something else. 90% stuff in the north and the backcountry. So anyway, maybe try it for another country if you want, and just see what you can get. But anyway, everyone, it was great to be hacking with you this Global Hack Week, and we'll see you soon. Great to meet you all, and happy hacking.